All right, so enzymes and chemical reactions. So it says, so we've talked about macromolecules. We just got finished with our quizzes about macromolecules, which are usually these nutritious categories let me say we find on the sides of our food products. As you can see, that is a nutrition label. Not sure if you noticed, but those macromolecules we've been talking about, yes, those are in almost every single thing that you eat. So you have your fats, your carbs, your protein, and of course, any and everything has a DNA source. They don't put DNA on the nutrition labels, not that serious. But of course, everything that is living has DNA. So they're your macromolecules. So the fact of the matter is, once we consume these macromolecules that we talked about, once we digest them in all the foods that we eat, our body goes through a chemical reaction to break down those big molecules. Macro means big molecules into tiny nutrients. Thus, they're called nutrition, part of nutrition. So let's talk about that breakdown, that chemical reaction, right? A chemical reaction is a process that changes or transforms one set of chemicals into another set, all right? So you have two sides to a chemical reaction. On the first side, you have your reactants, which are the elements that are going into the reaction, entering the reaction. And then on the other side, you have the products, the aftermath. So your reactants, boom, a chemical reaction happens, and then you have your products. So the products are at the end, on the other side of the reaction. For example, poop is a chemical reaction of food and your body's digestive system. So of course, you eat food, it goes into your body's digestive system. So those are the reactants. What is the product? Poop. So of course, a lot of times in the hospital, if I have a patient that comes in and they're saying that they haven't passed any kind of stool in a certain amount of time, immediately I know that there's something that either, one, they're not eating, and usually that's not the case, and two, that there's something wrong with their digestive system. How do I know that? Because I know that poop is a product of the reaction of food in your digestive system. So therefore, if I know you're eating, so check mark for the food, and you're not pooping, clearly the other part of the reactant isn't there. So something's wrong with your digestive system. So therefore, I will assess a patient's digestive system. Maybe they have a blockage, maybe something's going on with their stomach content, something. But again, that's how I know. There's a chemical reaction here, and if there's a part missing on the reactant side, I know that the product is not going to happen. So there you go. Unlike a mixture, chemical reactions cannot be undone. So yeah, I don't know if you've noticed, but there's absolutely no way you can undo your poop. Like I said, I like to use that example because everybody understands that pretty much. So that's pretty solid. All right, so you have your chemical reactions. So of course, you guys have once upon a time heard of this, the law of conservation of energy. You guys should already know by taking so many years of science that energy can never be created or destroyed. You cannot create new energy. You cannot destroy energy or throw it away. There's no such thing. You can only release or absorb it. All right? So of course, for example, in your chemical reaction, talking about your body's digestive system, you absorb your energy when it goes through your digestive system, and then you release it as you do your everyday things. When you burn those calories, you're releasing that energy. Okay? So within a chemical reaction, like your body digesting food, chemical bonds are formed or broken, and the energy is released or observed. Even the process of digesting your food uses calories, which is your body's way of measuring energy. So your digestive system even burns calories. So you absorb energy through your digestive system, but you also release it. And again, thus we get energy from those macromolecules that we eat, because again, they get broken down to be our nutrients, and those nutrients become our energy sources. All right. So let's talk about activation energy. All right. So in order for this digestion to even happen, we have to have some sort of energy, because either way, digesting food is a chemical reaction. So we need energy to even start a chemical reaction. Activation energy is that energy that we need to get the reaction started. As we mentioned in the law of conservation of energy, energy is either released or absorbed, right? So looking at these two charts, one of them is an example of an energy absorbing reaction, and the other side is an example of energy releasing reaction. All right. So for example, in the first one, which is an energy absorbing reaction is one that requires energy to be absorbed for the reaction to take place. All right. So before the reaction even happens, the chemical reaction needs to absorb some energy. So that's what the first one is showing. So it's showing the reactants are low, they absorb energy, that's that activation energy piece, and then the products happen once that energy gets to a certain height. So that's the kind of energy absorbing reaction. Makes sense because it's demonstrated by the graph. Now, in the other one, which is an energy releasing reaction is when energy must be released for the reaction to take place. So the reactions are high on the graph. Then you see that the activation energy decreases, that slant downward. And then the products are at the bottom. So I like to tell kids the easiest way to decide what the graph is you look at the product and the reactant. If the reactant is lower than the products, then you know that it's an energy absorbing. If the reactant is higher than the products, you know it's energy releasing, right? Because remember, it's before and after. So before the reactants, so if the reactants are lower than the products, so before it's low and then after it's high, that means it had to gain energy. Before the reactants are high and then the products are low, it had to lose energy. That's how you kind of look at that graph. All right, first activity. So this is a matching activity, and it's going to just literally go over what we just went over with the following terms. So again, matching activity, you are matching the term to its definition. All right, time's up. All right, nice job, Andrew. 6 for 6. All right, Marlon, you're pretty close too. Victor, nice job. Antonio, nice job. All right. So, getting back to that chemical reaction. So, however, when these chemical reactions happen in your body, at the end of the day, our body doesn't have time to wait for a chemical reaction. So if a chemical reaction is too slow or if it takes too much energy for that reaction to happen, our bodies naturally have these things called catalysts in them. So again, a catalyst is something that is going to speed up the rate of a chemical reaction. So again, imagine if it took like a really long time for us to get the nutrients from our food. Like if we just waited on the chemical reaction to naturally happen and it took too long, we literally would probably be moving like turtles because we wouldn't have the energy because it's taking so long for the chemical reaction, taking too long for our body to break down the food and give us what we need. So that's why our body naturally come up with these catalysts. So again, a catalyst is a substance that speeds up a chemical reaction. The catalysts work by lowering a reaction's activation energy. So remember that energy that is needed for the reaction to happen, the catalyst comes and cuts it in half. So we don't need half as much energy as we used to need. So therefore the reaction happens faster. All right? The less energy needed to start the reaction, the faster the reaction happens. So that's what a catalyst does. Cuts the activation energy in half so that it speeds up the chemical reaction. Right? In our bodies, those catalysts are called an enzyme. Right? So now we're getting into our other topic. We're talking about chemical reactions today and an enzyme. So again, in our bodies, those catalysts that cut the activation energy in half are called enzymes. Enzymes are proteins, so there's a macromolecule, so that's one of the reasons why we digest proteins in order to create these enzymes. Enzymes are proteins that act as biological catalysts by speeding up chemical reactions that take place in our body cells. Enzymes act, again, by lowering the activation energies for the chemical reactions that take place in our bodies. So again, it's the same thing. An enzyme is a catalyst. So an enzyme cuts the activation energy in half so that it speeds up the reactions that we need to take place in our body. All right. The chart here is just demonstrating just that. So the red line is saying how fast a reaction happens with an enzyme, and then the blue line is saying a reaction without an enzyme. Notice that the blue line is higher and it's taking longer for the reaction to happen. The red line is lower, taking less energy for the reaction to happen, therefore it happens faster. Right? So that's how you look at this chart. All right, so we're going to fill in the blanks here. Oh, morning. So go ahead and fill in the blanks based on what we just went over. Just me, so. I was just going to say, just me, so. Give it to everybody else who needs it. I haven't even touched them. Nobody comes in here. So nobody comes in here, so. Yeah, but you. So again, read the directions. It should be telling you that enzymes, our body's catalysts, the easiest way to identify an enzyme is because most enzymes have the ending of ACE, ACE, ACE. So, being that we know our macromolecules and such, you're trying to decipher what breaks down what. All right, next job, Kayla, Janaya, Antonio, Kamania, Andrew, next job. All right, so I'm going to move on from this activity. All right, so how does this work? So let's talk about how the enzymes actually cut this activation energy in half. So how does it happen in our bodies? So this process is called an enzyme substrate complex. That's what this is actually called. So that's what happens in our bodies in order to cut that activation energy in half so these chemical reactions can happen faster. So I'm going to break it down for you what an enzyme substrate complex is. So remember that there are two sides to your reactions. We talked about that earlier. There's two sides to every reaction. Hold on. Let me let someone in. Okay, never mind. They need to do that. All right, so there's two sides to every reaction. There's the reacted side, the reaction happens, and then there's the product side. The reactants of the enzyme catalyzed reaction are known as a substrate. All right. So for example, when we go back to that poop example, so the food and the digestive system would be known as the substrates because they're the reactants. So the food and so the food and our digestive system are going to be your reactants, also known as your substrates. So the substrate is going to bind to the enzyme at its active site, right? In this case, more than likely, we're talking about the food here. So the food is going to bind to the enzyme at its active site. Notice that that's shown here in the picture. So this is the enzyme. This little cubby here, that's the active site. And then this is the substrate, that little red thing here. And that is going to be, let's say, the food or the macromolecule. So let's say that's a carbohydrate. It's going to bind to the active site on the enzyme, and that is where the chemical reaction will occur. Okay? So the reaction happens, and then after, the products are released from the enzyme's active site. So for example, this one is showing you just that. So the substrate binds, reaction binds to the enzyme, reaction happens, products are released. So they're breaking it down. So let's say this is a carbohydrate binding to the enzyme. Carbohydrate binds to the enzyme, reaction happens, and then remember those building blocks. So this is probably two monomers, also known as monosaccharides for carbohydrates. Two monosaccharides are going to come out of this chemical reaction because now it broke down the carbohydrate to its building blocks again. All right. By the way, the active site is where the substrate binds to the enzyme. So again, that's the active site, the active site. This fitting of the active site and substrate is so precise that it's often compared to a lock and key, called the lock and key theory. So all it's saying is that that all enzymes have a specific shape, and those enzymes only break down that specific substrate. So like we did in that fill in the blank example, lactase, which is the enzyme, will only break down lactose. That's it. It will not break down anything else. So let's say a protein tries to come to the lactase enzyme, it won't fit, just like a key, the wrong key won't fit in a certain lock. So again, the special enzyme is only made for that special molecule or that special element. It will not break down anything else. All right, so if it's the wrong key, it won't unlock it. So if it's the wrong molecule, it won't get unlocked if it tries to bind to that enzyme. Okay, so that's a lock and key theory. All right, Kandinsky, go into the chat and you're using the Nearpod code to log into Nearpod. All right, so I'm going to have an open-ended question here. So it says, considering that lock and key theory that we just talked about, if an enzyme changes its shape, so let's say the enzyme changes the shape of its lock, what happens to its substrate? Think about that lock and key theory. If I was to change the shape of the enzyme, what will happen to what binds there? Put a second on the clock to get your answer in. All right, time is up. All right, so I'm gonna share some of you guys' answer because it is the correct answer. So nice job, Ashlyn. That is correct. Right. So if the enzyme changes its shape, then 9 times out of 10, the substrate will no longer be able to bind there. Exactly, Kamara, it wouldn't fit anymore, so therefore it probably wouldn't work. Erasable, right. So if the substrate cannot bind, then that chemical reaction can't happen. So yeah, it might go slower. Right, substrate won't bind correctly. Nice job, Tatiana. Victor, yes, but the substrate won't change its shape. So once pretty much, so we're going to talk about it in the next slide actually. So you're not wrong. Just the substrate will never change its shape. I'm going to discuss it. Right, will no longer bind, so on and so forth. So let's move on. More of you guys are right, don't get me wrong, but we have to move on. All right, so denature. So one last thing. So talking about, it changing its shape. So enzymes like to live in specific environments. So for example, those enzymes that are in our stomach acid, we have a lot of enzymes there because that's where, our digestion of our food happens. So we have a lot of enzymes. As a matter of fact, the organ in your body that produces a lot of those enzymes is called your pancreas. And your pancreas is super important. You probably have heard of your pancreas when you talk about diabetes. So the pancreas creates insulin, which breaks down sugar molecules. And of course, if you don't have enough insulin in your body, that's when you have diabetes because you have too much sugar in your blood because that enzyme is not there to break it down. So again, boom, here we are. Let's say, so again, a lot of enzymes like specific environments, likes it to be really acidic, likes to be really basic, likes to have it really hot, likes to be really cold. So there's stuff like, again, the pH level and the temperature are really big to enzymes. They want to have that certain pH or they want to have that certain temperature and they do not want it to vary, right? But let's say it does. So when an enzyme is pushed out of its comfort zone, meaning that the pH got too low or the pH got too high, the temperature got too low, the temperature got too high, it will become denatured. Okay? Denatured means that the enzyme has lost its shape and therefore cannot perform its duties. Right? So that was that question that I just asked you guys. Let's say the enzyme changes shape, what happens to the substrate? So what happens is because that enzyme changes shape, the substrate can no longer bind there. Nothing happens to the substrate except the chemical reaction can't happen, so certain things can't happen in your body. So remember that example I told you in the beginning. Let's say again, I know that the patient's not pooping, and I know that they're eating, so clearly something's wrong with their digestive system. Things like this can be wrong with their digestive system. The fact that maybe the certain enzyme that they had, maybe it's becoming denatured because maybe they're sick and their body temperature is too high, or maybe they've taken too much antacids, which is a thing that will calm down your stomach acid. Maybe they took too much of those and their stomach acid is too basic, so it denatured a lot of the enzymes. Things can happen in your body to throw things off. So again, if the enzyme becomes denatured, that means that the substrate can no longer bind there, and therefore the duties cannot be performed. So that will affect your body system. Again, now why can it not? Because again, because the substrate, aka the key, can no longer fit in the lock, also known as the active site, therefore the enzyme becomes denatured. So that is exactly why, again, a lot of you guys that shared your answer, if the substrate can no longer bind to the enzyme because it's changed its shape, then that means that those reactions will no longer happen. Okay, lock and key theory. All right, so let's use an application example. So it says a group of students decided to carry out, let me see if I can see the whole thing. Well, you guys will be able to see the whole question. So I'm going to read part of it to you guys. It says a group of students decided to carry out an investigation to find out how enzyme activity is affected by a temperature change. They put samples of salivary amylase into starch test tubes. Oh, I forgot to change that. Well, they put examples of amylase into starch and starch in 2 test tubes. So let me just give you some background knowledge. So amylase, notice the ASE at the end, so it's an enzyme. Amylase is the enzyme that breaks down carbohydrates, all right, breaks down sugars. And so they're putting starch, which is of course a sugar. Starch comes from potatoes, pastas, all that good stuff. They're putting starch into 2 test tubes, and they're putting amylase into 2 test tubes. So naturally, if you know that starch is a carbohydrate and amylase is an enzyme that breaks it down, we know that inside that test tube, that amylase is currently breaking down that starch. But these guys are going to vary the temperature. All right, so let's start the activity. All right, so the question is asking you guys, oh, show me the rest of the question. Why is this? Well, you guys can see the rest of the question. I can't, I don't know why. Oh, here it goes. So again, let you know, amylase is an enzyme that breaks down carbohydrates. It likes to be at a temperature of 37 degrees Celsius. What do you think happened to the rate of reaction when they increased the temperature of the first test tube to 37 degrees Celsius? So they made the first test tube, they increased the temperature to 37 degrees Celsius. Hint, hint, this particular enzyme likes to be at that temperature. So what is going to happen to that reaction? All right, so once you are done with answering this one, this is actually our last slide in the Nearpod. The next slide is just a link to quizzes so that you guys can do your water property quiz. Once you are done with this, please go ahead and I'm going to drop the code in the chat. And then go ahead and log into your quizzes and then break out your water property notes so that you guys can start studying for that. What just happened? Oh my God. So yes, I see that a lot of you guys have the correct answer. Well, no, not that one. Oh, actually, where did you get that answer from? So yeah. No, if it goes beyond that 37 degrees erase mode, that's when it'll be denatured. So again, ultimate, because it likes 37 degrees, those enzymes will be very active at that point. If it goes beyond that 37 degrees, they won't be, they will probably be heading towards being denatured. If it's too low, so it's too cold for them, then also they'll be heading towards being denatured. So anything that varies beyond the 37 degrees that they like, they're either going to be slowing down the reaction or it is going to start denaturing the enzyme itself. Right? So that's the answer I was looking for. So again, what's happening with the enzyme at 37 degrees? It's at its peak. So it's the most active at that point. So again, at this moment, the code is inside of the chat. You are logging in so that we can do your water properties quiz. I don't know if we'll have time though. The time. All right. Well, I'm going to go ahead and start it for those who already logged in. The code is still there. You can still log in.